In this problem, we're going to find the energy stored in the capacitor and the inductor. And if we remember, when we want to calculate the energy stored in the capacitor, it's 1/2 CV squared. The energy stored in the inductor is 1/2 Li squared. So we need to find the voltage across the capacitor and the current flowing through an inductor. And if we note, we've got DC sources. And if we remember, for the capacitor, I is equal to CD VDT. If the voltage is constant, then the current 0, that's like an open circuit. And for the inductor, V is equal to LDI dt. If the current's a constant, the voltage is 0, so that's like a short. So to do this analysis, we're going to go in and replace this with an open circuit and replace this with a short circuit. And our resulting circuit looks like this. We're going to calculate the capacitor voltage and inductor current. And if we look at the circuit, for instance, if we apply Kirchhoff's current law here, we've got 8 milliamps entering, 2 milliamps leaving, so that tells us that that current is 6 milliamps. So then that tells us that that's 18 volts across the 3K resistor. Now, if we look at this node and apply KCL, that says this current is IL plus 2 milliamps. Now, let's apply KVL around this loop. And if we do that, we're going to get 6K IL plus 2K IL plus 2 milliamps is equal to 12. And then we have 8K IL plus 4 equal to 12. Then that gives us 8K IL equal to 8. And then that gives us IL equal to 1 milliamp. So that tells us then that this current is 3 milliamps. And then that tells us that the voltage across this resistor then must be 6 volts. Now we can apply KVL around this loop. And if we do that, we'll have plus VC plus 6 minus 18 equal to 0. That gets us VC equal to 12. So now for our inductor, we'll have 1/2 times 1 times 1 milliamp squared. And that gives us 500 nanojoules. And then for our capacitor, we'll have 1/2 times 10 nanofarads times 12 squared. And that gives us 720 nanojoules.